Hi, my name is Przemysław Koprowski and this is the second part of a mini course of SageMath. Last time I showed you how to use Sage as a very advanced calculator, how to do some basic computations in Sage. Today we'll concentrate on calculus. I will show you how to work with functions, how to define a function, how to plot a graph of a function, how to compute a limit, a derivative and an integral. You define a function in basically the same way you define any symbolic expression in Sage. So suppose that we have a function that looks like this. Here ln stands for the natural logarithm. The first thing we need to do in order to define this function is to declare the variable t which appears in this function. We learned how to do it in the previous video. If you missed that video, then the link is on the top right corner of the screen. So I will type var of t and now I can define the function itself. So I will type f of t is a logarithm of 1 plus t times sine of t squared. We can now pretty print f using the command show we learned last time. So if I type show of f, I will see the f nicely displayed on screen. So that's what I will do right now. So I will type show of f is plus a LaTeX of f. So this gives us the original function f. Now the first thing we want to do with f is to evaluate it somewhere, let's say at pi over 3. So if we want to know the value of f at pi over 3, I just type f of pi over 3. As you can see, the result is given as a symbolic expression, not a number. The reason was explained last time. The Sage is symbolic oriented, unlike the program like MATLAB, Scilab, Octave, which are numerically oriented. So Sage tries to preserve a exact symbolic value as long as possible, as long as we don't tell it to just display a numerical approximation. So if we want a numerical approximation, we just call the method n that we met already, we encountered in the previous video. So if I type n of this expression f of pi over 3, then I got the real number which approximates a floating point real number that approximates the value of f at pi over 3. So I type f of pi over 3 dot n. As we can see, the value is roughly 0.6. The next thing we will do is to plot the graph of f at some interval. Actually, SageMath has really impressive plotting capabilities. It can plot 2- and 3-dimensional graphs of functions, of parametric functions, of implicit expressions, implicit functions. It can even do some animations, like the animation you can see on screen right now. The list you can see on screen right now just gathers the most common, at least in my opinion, graphic functions that Sage offers. Here we have just a function which goes from the real numbers to the real numbers, so we need just the first of these functions, so we need just the function plot. So I type plot of f of t, where t varies from 0 to 5. And we can see the graph of f. Alternatively, I can type also f dot plot from 0 to 5, and the result is exactly the same. The graphic objects in Sage can be combined using the operator plus. Just like you add numbers, you can add graphic objects together. So in this example, I will overimpose the graph of the natural logarithm of 1 plus t on the graph of f, so that we can see how the natural logarithm bounds the amplitude of f, so that we will see how f varies in the interval specified by this natural logarithm. To this end, I will call this graph, this graphic object, I will assign it to some variable, let's say p. So now if I display p, when p is this graph, I want to add to p the graph of a natural logarithm, so I will type p plus equals a plot of the natural logarithm of 1 plus t, where t varies over the same interval, so t varies from 0 to 5, and we need to display it, so I will type show of p. So here is the result. The line on top is the graph of natural logarithm, and we see how it limits the graph of f. It will be more clear if we change the color of this graph. So I will change the color of the graph of a natural logarithm to red. So I will type color is red, and I will also plot the lower limit of f, so I will plot the mirror image of natural logarithm. So I will type p plus equals plot of, and here I can just copy and paste the whole line here, except that I will change logarithm to minus logarithm, so I have a mirror image of this graph. Once we execute this cell, we see all these three graphs on the same picture, so we see how the graphs of these logarithms limits the amplitude of f. And now we will do something a little bit more challenging. We will plot the graph of the following function. Here the domain is two-dimensional, therefore instead of plot we will use plot 3D. So the first thing to do to plot the graph of this function is to declare both variables x and y. So I will type var of x and y, and now I can define the function itself, so I can type f of x, y is cosine of x squared plus y squared times the exponent of minus 1 times x squared plus y squared and divided by pi, and again I will display this function using show, so show f is plus a LaTeX of f. So I will now plot the graph of this function, so I will type plot 3D of f, where x varies from, let's say, minus pi to pi, and y varies from minus pi to pi. Here is the graph. As you can see, the graph is, of course, it's three-dimensional, but it's also interactive. You can rotate the graph, you can zoom in or zoom out to see the graph from whatever perspective you choose. In the previous example, we had a function that takes a pair of numbers, so a pair of arguments, and assigns a single number to it. So it was going from R2 to R, from the real plane to the real line. Here we will now consider somehow opposite example. So we'll consider a function that takes a single real number and produce a pair of real numbers. So it goes from the real line to the real plane. So for example, let's take a function that looks like this. To some argument t, it assigned sine of 3t and cosine of 5t. This way, this function defines a parametric curve in the real plane, and we can display this curve using the function parametric plot. So I will type f of t is, and it's a pair consisting of sine of 3 times t and cosine of 5 times t. I will display it again, show f is plus latex of f, and now I can plot this parametric curve typing parametric plot of f of t, where t varies from 0 to 2 pi, and as we can see the graph is this Lissajous curve. In a similar fashion we can also plot parametric curves, space parametric curves and parametric surfaces. So if we want to have a space parametric curve, we need a function that assigns to a single number a triple, so a point in a space. And to get a parametric surface, we need a function that assigns to a pair of numbers, so a point on a plane, a triple, so a point in space. So this space parametric curve is a function from R to R3, and the space parametric surface is the function from R2 to R3. So here, for example, I will plot torus defined as a parametric surface. Here on screen you see the parametrization of a torus. So I will type this formula into Sage. So first of all I will declare variables u and v, and then I will type function t. So let's start with declaring the both variables which appears in our formula. I will assign the inner and outer radius of the torus. Let's say it will be 1 and 3, for example. And now the torus itself is defined as a parametric surface by this formula. So this is r plus r times cosine of v times cosine of u. That's the x coordinate. And now the y coordinate is r plus r times cosine of v times sine of u. And now the z coordinates is r times sine of v. We can display it, show t is plus latex of t. And as I said, we can display this parametric surface using the command parametric plot 3D. So parametric plot 3D of t, where u varies from 0 to 2 pi and v varies in the same interval from 0 to 2 pi. And so you can see that we got this torus. The next thing I want to show in this tutorial is how to compute limits. Limits of functions, limits of sequences. So suppose that we have a function that looks like this, and we want to compute its limit at infinity. The corresponding Sage command closely resembles the standard mathematical notation, except that everything is written in a single line because it's how we type commands in Sage. The arrow is replaced by the equality sign, and since most of the keyboards out there lacks the sign of infinity, instead we type double lowercase o, because double o looks similar to infinity, so it's an easy to remember replacement. So let me type in this function definition and compute the limit. So I type f of x is sine of x times sine of 1 over x. Display it using show f plus latex of f, and now I compute the limit lim of f of x for x at infinity. As you can see, this function converges to 0 at infinity. In In basically the same way we can compute a limit of a sequence because a sequence is nothing else but a function just defined on the positive integers instead of on real numbers. So for Sage it's exactly the same if you compute a limit of a sequence or a limit of a function. The command that we use is precisely the same as the command lim that you saw in this example just a moment ago. So suppose that we have a sequence defined by this formula that you can see on the screen right now, and we want to find its limit at infinity. We haven't used the variable n so far. First of all, we need to define the variable, declare the variable n, and now we can define the sequence. So we can type a of n is the factorial of n over e to the power n square, and we can now display it typing show of a n equal to LaTeX of a of n, and we see this formula. As you can see on the screen, I type a of n instead of using a lower script for n. The subscript is the traditional notation for an element of a sequence. That's how we traditionally write it in mathematical texts, but formally, n is nothing else but the argument of the function a. So in Sage we treat all these cases in the same way. We just type a of n. Doesn't matter whether n is an integer or n is a real number. So as we typed f of t using the parentheses, so we type a of n again using the parentheses. However, traditionally in mathematical text we type a and put this n in the subscript because it's just the conventional notation. And we can now compute the limit of this sequence precisely using the same command. So I will type lim of a of n when n goes to infinity, and we see that this sequence also converges to 0 at infinity. A special case of a limit of a sequence is the sum of a series, because sum of a series of an infinite series is nothing else but a limit of partial sums. Sage offers dedicated command to compute sums of series, and it should not be really surprising that the function itself is just called sum. The short animation you see on the screen right now explains how to use this function, how to convert the standard mathematical notation into Sage command. So as an example, let me calculate the sum of a series of the form 1 over 1 plus n square. So I type s of n is 1 over n square plus 1, and capital S is the sum of this series, so it's sum of Sn for n varying from 1 up to infinity. I can now display this sum, so I will type show sum for n from 1 up to infinity plus LaTeX of S of n plus equals plus LaTeX of S. Everything that I type inside the quotation marks is sent directly to LaTeX. So here I can just use the LaTeX commands, except that backslash is used as an escape character. So if I want to type backslash, I need to type double backslash. So that's why I typed double backslash sum or double backslash infinity, because the corresponding LaTeX commands are backslash sum backslash infinity, and so the double backslash stands for the LaTeX backslash. If I now execute this cell, I see that the sum of 1 over n squared plus 1 is this formula. The result is again expressed as a symbolic expression because it cannot be evaluated exactly. The result is not a rational number that can be printed directly as a rational number. So it's some kind of a transcendental function psi. And we know what to do if we want to find a real floating point approximation. We just need to use the function n, the method n, to get the numerical approximation. So that's what I will do right now. I will type plus approximation plus LaTeX of s dot n, and this is the numerical approximation, and we see that the result only slightly exceeds 1. We can also combine these two commands, lim and sum. For example, if we want to compute the limit of a sequence which involves summation, limit of a sequence which looks like this, the numerator is the sum from 1 to n. For some new variable, we need some temporary variable that will be used in the summation. I will call this variable k, so I will declare k as a new variable, and the numerator is just sum of k cubed for k varying from 1 to n. So our expression is given by the formula a of n, the nth element of a sequence, is the sum for k cubed, where k varies from 1 to n, and this is divided by n4, and we can compute the limit of an, so limit of a of n, where n goes to infinity, and we can see that in this case the result, the limit, is 1/4. Now we will concentrate on the next fundamental concept from calculus, which is a derivative. Sage can compute derivatives of in any order of a function using the command which is called just derivative, or alternatively a second command is diff. Both commands do exactly the same, they are synonyms, so you can use whichever you prefer. So suppose that we have a function that looks like this. It's cosine of x squared plus 1 and sine of x squared minus 1, and we want to compute its derivative. We have already declared the variable x earlier, so we don't need to declare it again. Sage is already aware of this variable. I can just type the definition of the function. So I will just type that f of x is the cosine of x squared plus 1 times sine of x squared minus 1. And as always, I will display this function, so I will type show f is plus LaTeX of f. Now to obtain the derivative of f, I will just type df of x is derivative of f, and I can display that show f derivative is plus LaTeX of df. The formula is not simplified, so if we want to simplify it, we can use the function simplify full that we learned at the previous video. So I can type here, I can change this line and type df of x is derivative of f dot simplify full, and I can execute this cell again, and we got a simpler formula for the derivative. Alternatively, I can also write df of x is f dot derivative. That's exactly the same. I can use this derivative either as a function or as a method. Dot simplify full, and I will copy this line which displays it on screen. Ctrl C, Ctrl V, and we see that the result is exactly the same. If we need to compute a derivative of a higher order, we just specify this order as an additional argument, as an optional argument of the function derivative. So suppose that we need to compute the second derivative of f. So the second derivative would be f dot derivative 2, this is a second order derivative, and again I will simplify it, simplify full, and so we can see the second derivative of f. Alternatively, if we prefer this functional notation, so we want to write the derivative of f, then we would type derivative of f comma 2, so this is the second derivative of f, and again simplify full to get the simplified expression, and the result is of course the same because it is the second derivative of f. In a similar fashion, if we have a multivariate function and we want to compute derivatives with respect to specific variables, we just specify these variables in parentheses as I specify the order of the derivative. So for example, let's take the function that we have already used today, so the one which to a pair xy assigns the cosine of x squared plus y squared times the exponents of minus this sum over pi. I will copy this function from the previous part of this notebook. This function is defined here, so I will copy this cell and I will paste it here. Now if I want to compute the first derivative of f with respect to variable x, I will just type fx is f dot derivative with respect to x, and we can display it, show, and again everything which goes into the quotation marks is just a latex, except that backslashes must be doubled, so I will type frac of partial of f over partial of x, so this is the derivative of f with respect to variable x, and this is a latex of fx. And as you can see, this is the derivative of f with respect to x. If we want to compute mixed second order derivative, we just specify the variables one after another. So for example, if I want to compute the second order derivative of f with respect to first x and then y, I will just type f dot derivative first with respect to x and then with respect to y, and I will just copy this line and paste it here, but I want a second order derivative, so I want partial square of x with respect to x and y, and this is fx y, and this computes the second order mixed derivative. In the last part of today's tutorial, I will show you how to compute integrals in Sage. Sage can do both definite and indefinite integration. The command used to compute the integral is, well, as you can see, called just integrate. Or integral, both commands work the same, so there are two commands, integral and integrate, and they do exactly the same thing. So for example, suppose that we have a function that you can see on the screen right now, and we want to compute the indefinite integral of this function, so we want to compute antiderivative of this function. I will type the definition of f, so f of x is minus sine of x times cosine of x over x plus 1 minus cosine of sine of x over x plus 1 square, show f plus latex of f. And now I will compute the antiderivative of f and I will assign it to capital F. So I will type capital F is f dot integrate. Here, in contrast to the derivative, we must explicitly specify the variable. So I must write that we want to integrate with respect to the variable x. And now we can display this antiderivative. Recall that the later comment for displaying the integral is int, so the integral of f with respect to x is latex of f of x of capital F, and we see that this is the integral. If we want to compute the definite integral, the limits of integration are passed as additional parameters of this command. For example, if we want to compute the integral over the interval, let's say pi over 4 and 2 pi over 2, I will copy these two lines, paste them to a new cell. I will call this definite integral I. So I is the integral of f from pi over 4 up to pi over 2. And now I can display this here. So we have this thing. Again, the answer is returned as a symbolic expression for exactly the same reasons as before. And we can again approximate it using the method n. So if we want the numerical approximation of this integral, I will follow this I by dot n and empty parentheses. So I will type here plus approximation plus latex of I dot n. The result is roughly minus 0.2. Here we use the same approach as before. So first we evaluated the expression exactly and then we approximated it numerically using the method n. This works, however, in this case, when we compute the definite integral, there is a much better method. The better method is to compute the integral numerically from start. So instead of finding the symbolic expression and approximate this expression numerically, we compute the integral directly numerically. This method has two obvious advantages. First of all, it is more numerically stable, it's more reliable. If we compute the integral numerically from scratch, then the approximation is usually better than when we evaluate it symbolically. We got very complicated symbolic expression that we then successively approximate. The second advantage is that the class of function that we can integrate symbolically is far more narrow than the class of functions that we can integrate numerically. The class of functions for which we have a numerical integration algorithm is far broader than the class of functions for which we can find exact antiderivatives, and this is the only method we can integrate symbolically. So now let me show you how to integrate the function numerically. To this end we will use another SageMath command which is called numerical integral. So I will type numerical integral of f at the same interval from pi over 4 to pi over 2. The result is a pair of numbers. The first number here is the same as we obtained here, This is the numerical approximation of our integral, and the second number is the approximate bound for the error. So we know that this value here is not farther from the exact result than this value, so up to the 15 decimal digits this value is precise. As a final example today, I will show you how to visualize this integral. Recall that the definite integral is nothing else but the signed area between the graph of a function and the horizontal axis. So we can plot this area using the command plot that we learned today at the beginning of this tutorial. So I can plot the graph of f dot plot of pi over 4 to pi over 2, and if I add an additional parameter fill and I assign it true, this means that the area between the graph and the horizontal axis should be shaded. So we see that this shaded feature has the area equal to our integral. The picture will probably look a bit better if we extend the graph beyond the integration limits. So I will combine this picture with the second graph of f dot plot on a wider interval. So I will plot f from, let's say, 0 up to pi. So the resulting feature shows the graph of f together with some shaded area which equals to the definite integral that we computed above. So this gives us a natural geometric interpretation of this definite integral. This way we can visualize, explain what this integral actually is. So that's it. That was all that I wanted to show you today. I hope you enjoyed this tutorial. You learned something new, and so thank you very much for your attention and see you next time. Goodbye.